you don't know what happens inside, or you sort of know what happens inside, but you're not really sure what happens, and you have no access to data from companies that use this stuff, and that makes the problem very hard. But we sort of decided to engage in this process, and a lot of this is on the verge of being really art, and we think we got to some good conclusions, and I think Praveen really did a good job in executing all this. Most of the work, everything was done by Praveen. Most of the help was by Larry and Ivan, and then maybe me. So I'd like to thank all of you, and especially Praveen, so please go ahead.
Thanks a lot, Dr. Rssi, for that wonderful introduction. Before I get started, I think it's my pleasure to acknowledge a few people, a lot of the people actually who have made this thesis possible. As Dr. Rssi said, he's my graduate advisor. He has been supportive and helpful and throughout my graduate studies, not just in executing the thesis, but in terms of selecting courses and everything. And I really appreciate that help, and I want to thank you for that. Next is Dr. Larry Greenstein. I think Dr. Rssi said that Dr. Greenstein was really the person who worked, I think, most closely with in this particular thesis. And he has really led me, inspired me, through help, support, and a lot of, I think, adjectives that I can use. But I think all those are really inadequate to express my real gratitude towards him. Next is Ivan. I think graduate students in WINLAB would know how difficult it is to get a time slice of Ivan and talk to him. But I think everyone understands it's very important also in terms of getting advice from him. And I think I've been very fortunate. Ivan has been very kind in giving me a lot of time and advice. And I think without his help in doing not just measurements, a lot of things, this would not have been possible. So thank you for that. Dr. Ray was the person who actually led me to this particular thesis topic. He said, okay, we should look at ODM models and then see what is the throughput performance. And I think it was a wonderful, great problem, and hopefully I can convince you that this is actually a very interesting problem also. So I want to thank Dr. Ray for that. And then again, a lot of WINLAB students, many of them, I think without the friendship, I guess life would have been very difficult. So I think, thank you all. A lot of people, especially Jaspinder Singh, Rita Roy, Natalia, a lot of people, and I'm sure there are a lot more people who I want to thank, faculty, students. I want to thank everyone for various help that they did various times. With that, let me get started with the thesis presentation. So today we are going to talk about a method for predicting the throughput characteristics of wireless LANs, which have multiple rates. That is essentially the thesis topic. So before we go into the details of how we do that, this is the high-level picture. What is the main aim of what we are trying to do here is we want to develop a simple and accurate method for predicting the throughput characteristics of this rated active wireless LAN. So the method is generic. And so the predictor that we're going to develop actually should predict the throughput statistics, including mean or CDF, given the distance from the access point and the type of environment that you're operating in. That is the basic aim of our thesis work. And here's the general approach that we take. We said we are looking at a general approach for many rated active wireless LANs. So specifically in this work, we look at one of those very promising rated active wireless LAN technologies, which is IEEE 802.11a. And the basic approach is pretty straightforward. We know that average received power or variants of that, this could include RSSI again stands for received signal strength indicator. We'll see more of that. Or SNR. These are all, we know these are all good bases for predicting the throughput. So what we're going to do is we get this basis and then use particular information and macular information to convert it to a throughput number. That is the essential approach. So this work is actually, the rest of this work is going to be focused on developing a throughput predictor for 802.11a models, which uses a limited set of measurements, physical simulation results, and some macular analysis. Again, we have to keep in mind that this is the method that we develop is going to be very generic. We'll see how generic it is. So here is the outline for the rest of my talk. First, I will talk about why is it that we are interested in solving the problem. What is important? Next, I will talk about some of the methods which are available currently to predict throughput characteristics of rate adaptive wireless LANs. Then we'll present a very brief overview of IEEE 802.11a standard. Then we'll go to the measurement section where we present three kinds of measurement results: throughput, received power, and RSSI. Okay. From that, from the things that we learn from measurements, we go to the central part of the thesis, which is the development of the throughput predictor. So we start with a very high-level overview of what is the throughput predictor, what does it look like, and then we go to each of the individual blocks in the throughput predictor, which are physical layer simulation results, MAC layer analyses, and then finally we conclude by giving a packet level simulator and how actually it does the throughput prediction. Next section is results, so where we essentially present the throughput prediction results that we obtain from the throughput predictor. Results are essentially what we do here is we compare the throughput prediction results with the measurement results that we have, and this is to sort of establish that the method is accurate in prediction. And we also compare it with what is the ideal throughput performance, meaning what is the maximum achievable thing that you can get using IEEE 11a. We conclude this talk with main contributions that we make, some of the sample applications of our tool that we develop, and also with some directions for future work. Let's get started with the motivation as to why is this problem important to solve and important to solve. This is something which we all know that wireless LANs are becoming more and more popular, and we can in short, without getting into a lot of details, numbers, we can say wireless LANs are really becoming the networking method of choice of future. Naturally, there is need for developing simple as well as accurate throughput prediction methodologies for this wireless LANs. That's what we are doing. And what makes this problem? What is unique about a throughput prediction for the system that we are considering? It is a unique characteristic of the system, which is that the system is rate adaptive, right? And what this rate adaptive means is that all the systems will have a range of different rates, and it offers. So, for example, IEEE 802.11a offers 8 different physical layer rates, right? Starting from 6 megabit per second, going all the way to 54 megabit per second. So, any packet that is transmitted could be transmitted with any of these different rates. So, the system sort of assumption is that it adapts according to the channel conditions and different things. So one important part, as you can already see, is actually this rate selection algorithm, which means how do you actually select what rate to assign for each packet that is transmitted. That algorithm is called the rate selection algorithm. I think the most interesting thing, as Dr. Predrag pointed out, is that this is in most cases it's vendor specific and unfortunately unknown in most cases because cards and companies won't give the details. And that makes it a particularly challenging problem to solve. However, we cannot in any way ignore the impact of this rate selection algorithm on the throughput performance. We know it has a big impact, so we have to somehow model it. The way we are going to, the way we intend to do it is do throughput measurements. Do different sort of measurements, and from the measurement observations, we hopefully learn some things which we can use regarding the rate selection algorithm. Going ahead, here are some of the methods which are available currently to do throughput prediction for rate adaptive wireless LANs. There are essentially two classes of approaches, right? One is the measurement-based approach, where what people do is they do extensive throughput, extensive measurements using commercial modems and in a specific environment. So they would get throughput, they would get curves corresponding to throughput versus received power, or throughput versus SNR, or RSSI, whatever. And from this correlation curve that they get, they can use path loss models and then look up the curve and predict what is the throughput performance. And naturally, the thing about one advantage of this method in general is that it has got good accuracy for the specific measurement setup we are considering. However, the problem is that once we change that specific setup, for example, we change the card that we used to measure, or we do in a different environment, results might not be all that accurate. So we might have to redo all the extensive set of measurements. That is the drawback of this model. Then there is this analysis-based tools which are available. Essentially, here we evaluate the throughput as a function of physical layer performance, the MAC layer parameters, and all this sort of things. And naturally, this method is easy to use because it's all in equation form. You can just plug in numbers and get throughput numbers at the output. It makes it easy to use and extendable to some extent. However, they normally fail to capture the practical aspects of throughput prediction. For example, we will see in our work that most of these actually fail to make any assumptions on rate selection algorithm. They assume an ideal algorithm, which makes the results that they get a sort of an upper bound on the throughput performance. They don't really get the actual throughput, but sort of an upper bound. So essentially, poor accuracy in general. Our approach, what we want to achieve in our approach is actually we want our predictor to be accurate in terms of capturing the practical aspects, for example, rate selection algorithm. And we also want it to be simple, meaning we don't want to take extensive set of measurements each time we want to have measure the throughput. Right. Here is a brief overview of IEEE 802.11a standard, just as much as it's needed to understand the remainder of the work. 802.11a is a high-speed wireless LAN standard in the 5 GHz unlicensed band. The physical layer of the standard is based on a technology called OFDM. Most of us are familiar with that, orthogonal frequency division multiplexing. The basic idea is that this whole channel is broken down into narrow subchannels, and in each of these narrow subchannels, the frequency selective fading sort of appears flat. That is the basic idea. And also the physical layer supports multiple transmission rates, going all the way from 6 megabit per second, which uses a combination of BPSK modulation plus half-rate convolutional coding, to 54 megabit per second, which uses 64 clamp and quarter rate, 3/4 of rate coding. And the MAC layer of the standard essentially is based on, like any other 802.11 standard, is based on the CSMA technique. And it also supports retransmissions. Right? So if there is no acknowledgement that is that you get for the packet you transmitted, the MAC layer retransmits packets. That is also important. So now we get to the measurements part. So here is a brief overview of what measurements we do and why do we do this measurement. So as we said, the main aim of doing the measurement is to actually get a basis for throughput prediction. So for that, here are the different measurements that we do. Throughput measurements, the main idea is to find the throughput by distance performance in different environments. Then we do receive power measurements, where the basic idea is to verify that the environments that we select are typical, in the sense that they reflect the most general environments that one would find if you were to use wireless LANs. We also want to relate this receive power values with the throughput values that we have got. The next part is Rssi measurement, and here we want to relate the Rssi measurements with the other two values, the throughput and the receive power values that we get. And again, here is the place where we investigate. Can we know anything more about this black box, this sort of rate selection algorithm that we have to sort of model the impact of, right? And for all the measurement that we did, here's the same set of measurement environment that we use, and this is the diagram that describes that. We did measurements in 3 different environments. 2 of them were indoors, 1 of them was outdoor. The indoor environments were all inside the WINLAB building, this particular building. The indoor line of sight was done in the WINLAB, this main WINLAB corridor, which is here right outside. Access point was kept at one end of the corridor, and the measurements were taken across the length of the corridor. Right? In the non-line of sight case, the measurements are done inside the computer lab, WINLAB computer lab. And for the outdoor line of sight scenario, all measurements are done in the parking lot right outside WINLAB when it was empty. And in general, all these measurements are done in somewhat controlled environment, meaning when there are no people moving around and when there are no vehicles moving around, as much as possible. I think most of the measurements are sort of done either weekends or nights, so that not a lot of these movements are there. Going to throughput measurements, our basic aim is to measure throughput, which is given by information bits per unit time over the 802.11 wireless LAN. And we want to make sure we get enough averaging. We just don't report a number which is some random. So to get enough averaging, we did for each of the distance point that we saw in the previous figure, we have 3 spatial samples, and we also have 3 time samples. So essentially, for each point that we saw before, we essentially get 9 different sample values. And again, this is for one measurement set. We'll repeat this measurement set over multiple days so that we make sure we have it averaged out. The hardware that we use for measurement is we use the Intel access point and SMC 802.11 wireless card. Throughput measurement software, we use 2 different kinds. One is called iPad, which is a free download from the web. Other is called Chariot, which is a commercial software that we have. The TCP window size in both cases was set to 256K, and the packet length was set to 1,500 bytes. Sure.
3 spatial samples.
Yeah. So, okay, let me just go back here. And so when I say 3 spatial samples, what that means is that, for example, for this distance point, I measured here, this next spatial sample is going to be to the left of it, other is going to be just to the right of it. That is how I get 3 samples. Here is the throughput by distance curve that we get from our measurements. X-axis is distance in a log fashion, and y-axis is the throughput in megabit per second. Right? A couple of observations that we can make here. One of them is that if you see the throughput varies for any given distance point, right? The throughput variation for outdoor environment is lesser as compared to the variation for both the indoor environments. That's one point. The other one is that if you see, this is the indoor line of sight scenario, right? So we see that in terms of throughput corresponding to a given distance, throughput for indoor line of sight is more than the outdoor line of sight free space throughput that you know. So this is sort of a surprising thing that we initially found. The other thing is what I mentioned is that we are made to believe that 802.11a can deliver 54 megabit per second, right? But if you see here, the maximum that you can actually get at the application layer is just 20 megabit per second. So this is something which is again surprising or shocking. Then this is what is the packet transmission distribution. We have seen that as we've seen, the MAC level standard supports retransmissions. That's why this transmission distribution is important, right? To explain, on the x-axis we have transmission number, essentially transmission attempt, and on the y-axis we have success percentage for each transmission attempt. So what this sort of graph shows you is that 90% of the packets get transmitted successfully in the very first attempt, right? Or the very first time the packet is transmitted, 90% of them go through. Only the rest have to be retransmitted. That's what it shows. So this is actually for a specific distance, specific environment. However, we find that this distribution is sort of invariant to the, relatively invariant to the environment or distance that we measured it at. So this would look the same any environment, any distance at least for our measurements. And that is sort of, that tells us something about the rate selection process, right? Because that sort of says that, okay, whichever place you measure, whichever place you are in, 90% of the packets, for 90% of the packets, the rate that is selected is correct. That's why it's actually going through 90% of the time, in a very rough sense. Right? So that sort of says something about the rate selection process that is going on, that it is adaptive at least. Going to the received power measurements, or aims are to obtain the received power-wise distance, right? So that we could, this would automatically lead to path loss modeling results. And also we want to find what is the variation of received power in different domains. We'll see the results. And the hardware we used, the transmitter remained the same, internal access point, and the receiver in this case, instead of the card, it is a HP spectrum analyzer. Here is the received power distance plot. Again, distance on the x-axis, y-axis is the received power in dBm. We can make very similar observations as we did in the throughput case here also. Starting with, we see that there is very little variation for any given distance point for the outdoor environment. Whereas for both indoor environments, the received power really varies a lot, even for a given distance. The other observation that we made again is the slope of this indoor line of sight curve is much shallower than the slope of this free space curve, right? Or at least the outdoor curve. That is again somewhat surprising, but we'll see in the results and we'll explain why that is the case. Yeah.
Why you look the indoor long side that are seven while the other two curves start from 0.
Oh, okay. Just because there is a particular offset distance, because this non-line of sight scenario was such that there is an offset distance.
You can't come closer.
You can't come closer because there won't be non-line of sight if you come very close. Yeah. So here's the standard path loss model that all of us would have seen. It says path loss at any given distance d, right, equals the reference path loss. Reference distance was selected to be 1 meter here. And here's the propagation loss exponent that we want to find, and send log to the basin of the distance. Plus, here is the log normal shadowing parameter that we have to, essentially we have the variation about the mean. Here are the path loss modeling results for the plot that we showed. So this n number is really the slope of the curve that we showed before. So we see for outdoor line of sight case, as you would expect, this value corresponds exactly to 2, which is the free space value. Right? This is something which is good and which is expected. For line of sight, we saw the slope was shallower, and again, that's why the value of n is equal to 1.1, right? And this is sort of an artifact of the fact that in the line of sight case, there is this bars on both the sides, so this hallway acts as a guiding structure, thereby making the path loss much less. And for indoor line of sight, higher exponent of 3.1. And this table sort of shows the received power variation. We said we have done spatial time and frequency measurements. So we want to see how much does the received power vary if we fix the distance corresponding to the space, time, and frequency. And all these numbers here are the standard deviation of the received power variation. Right? How much does the received power vary in terms of standard deviation? So, for example, for the outdoor line of sight case, this says that over different spatial values, the standard deviation of the measurement was 1.2 dB. Again, so going to the observations that we can make from received power measurements, we have seen that the path loss response values that we get are sort of indicate that our environments that we measure are typical, meaning this result we have seen elsewhere in other people's measurements also, and these environments are very representative of the general environments that we would find. Also, this table sort of shows us that, again, confirms that both indoor environments have a much higher variation as compared to the outdoor environment, right? And this is good because this sort of correlates very well with our throughput measurements. We saw in throughput that indoor environments have a higher variation. This result sort of correlates very well with that. Okay. Going ahead, RSSI measurement. So RSSI stands for Received Signal Strength Indicator. So what is RSSI in 802.11 standard, right? RSSI according to the standard is a measure of the energy that you observe at the antenna when you receive a physical error packet. So this is, you can say, okay, this is some card surrogate for the actual received power. Right? The standard says that it should be a monotonically increasing function of the received power. However, the standard does not specify an exact relationship. So it's up to the vendor to say, okay, how do I convert from RSSI to dBm? For example, Atheros has this particular conversion rule. Take the RSSI value, subtract 95, and you will get the dBm value. So why are we doing this RSSI measurements? It's because we have certain theories about RSSI, that RSSI is correlated to some of the other measurements that we make. So let's see what they are. We think that RSSI is actually related to the physical error rate of the packets, right? And if this is the case, I mean, if we can verify this sort of tells us a lot about some assumption that we could make on the rate selection process. And we think that RSSI is related to the throughput. And if this is, and again, if we can verify this part, this sort of shows that RSSI can be used as a good basis. Right? As we said, one of the important aims of measurement was to find a basis. So we say, okay, RSSI is a good basis. And we also think that RSSI is related to the received power. This is quite natural. Why? Because at least the standard says that it should be correlated. So and if that is the case, we could use all the path loss modeling results to predict the RSSI, from received power to the RSSI. So here are the things that we want to verify, and we'll see in measurements how we do that. So here, this plot shows the RSSI measurements by this time. We used SMC card and Intel access point to do the measurement. So the first plot, this one shows the RSSI measurement, how it varies over time for a given fixed distance value. And this shows simultaneously how the physical error rate varies over time. This is again physical error rate, not the throughput. Okay, how it varies over the span of 4.55 seconds here. So it's very obviously we can make these observations that we see very large variations for both the RSSI as well as the physical error rate this time. We wouldn't expect that sitting at one constant place, we would have so much variation in RSSI and so much variation in physical error rate of the packets that are transmitted. Okay, and we also see that there is not much of a correlation between instantaneous values of physical error rate and that of RSSI. Okay. So we say, okay, why don't we look at the time average value of RSSI and time average value of physical error rate and see if they are correlated. That's what we are going to see in the next plot. Time average RSSI and physical error rate. X-axis is average RSSI, time average, and y-axis is average physical error rate, again with respect to time. So we see that again. Here we see there is a very nice correlation between the time average values of RSSI and physical error rate. Right? We see that even for a short time window, this is the case.
What was the time duration?
We have verified time durations as small as 3 seconds, but this is because our card reports measurements only 3 milliseconds. This measurements separated, the minimum granularity was 3 milliseconds, so we couldn't go down to that extent. But still, we are sure we could do it with 3 seconds. So this plot probably is for 3 seconds actually. This also suggests that. So what this also suggests is that average RSSI can be used to model average physical error rate selection, right? So if you have an average RSSI value, we sort of know what would be the average physical error rate that would be used, average again. However, we don't want to say that, okay, this confirms that, this is the way the card is selecting the rate. That is something which we don't want to confirm, again, which we don't know. However, this is an important observation which we'll use later in our throughput predictor. Going ahead, throughput, here's the correlation between average throughput and average RSSI value. Again, we see for both the environments, both these values are fairly correlated. And what this sort of shows is that this is RSSI could be the basis that we are looking for. We can do throughput prediction based on average RSSI value. That is what this plot conveys. Yeah. It's all for single user. Yeah. If it's not clear, there is no multi-user scenario. It's all for just one user in the system.
Also, you have to disable the ads in the
No, ACs are on.
What length?
I'm sorry?
And how many, what is the max number of access?
Maximum number of acknowledgements.
For each package and how many times could it be transmitted?
How many times could it retransmit? The number was set to 8, I think. 8 was the maximum number of times it could retransmit.
Well, I believe we never saw more than 6.
We never saw more than 6, yeah, but the maximum number was far more than that. Okay?
Praveen, this
Yeah.
is 20 to 60, is that increasing signal strength or decreasing?
That is increasing signal strength, because if you see if you will see in the next plot, the signal strength is found out by just subtracting 95. That means this is good question. This is actually increasing signal strength, yeah. And we would see increasing throughput also. So, sorry. So this is the next plot, which shows the RSSI value and received port. So as you said, we want to find out if they are correlated, right? The RSSI, the received port that we measured already using the spectrum analyzer is correlated with the RSSI value that we measure using the card. Okay? And we observed that for the outdoor line of sight, which is shown by this blue points here, they are fairly well correlated. The values are almost the same for outdoor line of sight scenario. For indoor non-line of sight values, they are correlated. However, there is actually a shift in the correlation, right? Almost a 4 dB shift here. So we'll see how we will deal with that later. However, the general conclusion is that they are correlated. Yes, we can, and that means that we can predict average RSSI based on path loss models, right? If you can predict this, we can also predict this. That's what it means.
Just one question.
Yeah.
You previously showed that DVM was RSSI minus 95 for some cards.
Ethros card, and we have used Ethros cards for our
But
measurements.
then that doesn't hold for this. So you're saying that's not accurate.
So what we are saying is that the formula is accurate for outdoor environment, whereas for indoor, that value is not exactly accurate. So instead of 95, it could be 91 or something like that.
They didn't specify all that in there.
What they claim is it's the constant for all environments. That's what they claim. But we find that that is not probably the case for all environments. No. That's a good question. The thing is, it really points to we don't have a clear explanation of why this is the case. Why RSI would be this thing would be different for different environments. However, we think it's probably due to the specific way in which RSSI is actually measured inside the card, and also due to the fact that there is a lot of variation indoors, and as compared to outdoors. So the next plot shows again average RSSI versus packet error rate, the average packet error rate for both the environments. Interesting observation we make here is that we see packet error rates are most of the time constant in between 0.1 and 0.2. There is not a lot of variation in packet error rates. What is, if you see, this is over a whole range of RSSI values. The packet error rate is fairly constant. And what this sort of suggests is that the physical error rate is chosen so that the packet error rate is almost a constant. And so there is a rate adaptation going on, rate selection going on, and so suggests that the card is selecting the rate so that packet error rates are almost kept a constant by selecting rates appropriately. And so here are the various conclusions which we have made.
What was the packet size?
1,500 bytes.
They're all your results
Are 4,500 bytes. And so you can hear in one slide all the measurement conclusions and how we could probably use them to build the throughput predictor that we have to build. Right. So we saw that RSSI can be made as a good basis for throughput prediction. We saw that we can use path loss based models to predict the average value of RSSI. Right. And we also found out that RSSI value is not constant, it actually keeps varying with respect to about the mean with time. And regarding rate selection, here are a couple of things that we learned. Average physical error rate can be based on a time window average of the RSSI. It has to be done also, the physical error rate selection has to be done so that packet error rate is kept nearly a constant at 0.1. This is the thing that we learned from our measurements on the rate selection. And all these things will actually, we'll combine all these things to see how do we actually build a throughput predictor based on these observations in the next slide. So here's a general overview, a flow chart which shows, okay, how does a throughput predictor work? Okay, so we start off with this average RSSI predictor model, which predicts the average RSSI value given a particular distance and environment, using the path loss modeling results, and also using a limited set of RSSI measurements. We'll again go into details later. And once we have the average value, we know we have to have the variations about the average. So we sort of simulate those variations here. And then we sort of find the time window average RSSI values. Right? And now we can select the physical error mode based on this time window average of the RSSI and based on the fact that packet error rate is 0.1, and for which we use some physical error simulation curves. And once we select the physical error rate, and once we have the average sort of RSI or average sort of SNR, we can find what is the probability that each packet will be dropped. So we probabilistically go simulate and drop each packet with that probability of error, again by looking into the physical error simulation curves. Once we do that, so see that here we sort of get a packet error data, which consists of physical error rate of the different packets and if the packet was actually a failure or a success. And based on this, we do some MATLAB analysis based on some MATLAB parameters of the standard, and finally we convert it to a MATLAB throughput value at this point. Okay. Once we get the MATLAB throughput value, we can, this plot sort of essentially does some sort of scaling to get the application layer throughput, because that's what finally we are interested in. So finally we convert this distance and environment to a throughput number. We'll see, so the next couple of slides will explain some of this graphs that you see here and see how exactly they work. First of them is how do you generate the RSSI values? We said we can base it on path loss models, or these are developed a path loss equivalent model for predicting average RSSI value. Start with the basic path loss model that we saw before, and then we say the path loss equivalent value for any given distance equals the path loss value at that distance minus a correction factor. This is a correction factor based on environment, and this is the factor that you would measure, that you would actually measure based on RSSI value. This is the 4 dB, the same thing that you asked me. This is the sort of the 4 dB value that you see. So for example, we see that for outer environment, the values match. So this value would be 0. There's no correction to be done. Whereas for indoor environment, there is some amount of correction to be done here. And now, based on this path loss equivalent, we can find the average RSSI value as transmit power minus this path loss equivalent value. Plus this is the conversion factor, right, from RSSI to dBm. For example, for the heteroscop, this value would be 95. And once we have the average value, we can simulate the variations above the average with respect to time by adding a random variable here. So this is actually we modeled it as an independent sequence of uniform random variables with a standard deviation of 3 dB. Again, this number is from the measurements, Rsl measurements that we have.
So you haven't explained motivation for using U. You haven't even talked about U.
So yeah, so
you haven't even talked about why did you choose the uniform.
Let me. This is actually a Gaussian normal Gaussian random variable, zero mean unit variance. So this is actually the standard deviation. So the sigma values we saw in the path loss modeling results. We didn't actually put it here, but the sigma was the standard deviation of the variation, which we saw in the path loss modeling table. This is a uniform random variable. Uniform Gaussian, normal Gaussian. And the next question was why did we select a uniform random variable to model the variation? The answer is that we looked at the variation, we saw if we could fit on the variation in general with any distribution. Can we model it as a Gaussian? The answer was we couldn't actually fit it. For different distances, we couldn't come up with the same answer. So for some it looked like Gaussians, for some it looked like some other distribution. So that's why we said, okay, we would actually, so in the absence of any more information, the best bet is actually to use a uniform random variable. Any more questions?
I think the variable in the SSI, the random variable, is dependent on the time.
You mean this random variable? Yeah.
T a time index?
T is the time index. You're right.
So I think maybe a shadowing should also account for the basic variations, you know.
So this is you're fixed at any given distance, and you're just looking at different time instance. So spatial variance would come when I would go from here to this point. So this,
if everything is fixed, as time goes along, it also should be a constant variable.
This random variable is.
I think because it is to shadowing, it should not be related to time.
The shadowing thing is actually taken care of here. This is the spatial variation, the shadowing thing that is taken care of here.
The equation, the two equations with here.
This equation?
Yeah. This is only a random variable in your formula there.
Right, true.
And you think there is some relationship between the path loss and SI. So I think there should be some equivalent term in these two equations.
I think Michelle is saying, why are you getting a random variation there when
There is
PL is
not.
fixed?
Right.
When this is fixed, why are we getting this variation?
What distance is fixed, is it?
Yeah.
Yeah.
Why are we getting the
Everything
variation?
is stationary, it's still RSS, the little RSSI.
Variation.
Right, yeah.
That's a very good question. The answer is that we don't really know what is the answer. I think
The black box.
Right.
But
So
it's usually something and we don't have explanation
It
why.
models the measurement of the RSSI inside the car. And
I mean, we really don't know how exactly are they measuring the RSI value and how exactly are they reporting the RSI value. And unless we know exactly how they do it, we can't say a lot more about that. It could be because of variations that happen in environment, but again, we don't think so.
So maybe in the black box, there may be some time dependent phase variation.
Time dependent thing, yeah, true.
Noise.
Noise, yeah.
Noise.
Again, but it's true that we don't have a very clear explanation as to why we see that huge variations. Going ahead, so we said we have to use physical simulation results at various points. So here is this plot sort of shows the SNR, or is the packet error rate for different physical error modulations of 802.11a. And the software that we used for getting this plot was actually a Cadence SPW 802.11 wireless LAN library. So the library was made to do different runs with different modulations and to give this numbers, these numbers here. The channel model that we used was a WGN channel. The packet length again was equal to 1500, which is the same as the measurements that we did. And this SPW library was modeled to have the impact of some practical aspects of throughput, some practical aspects of modems that you will see. For example, there was a frequency offset between the local oscillators of the transmitter and the receiver, which was at 100 kilohertz. And there was actually a channel estimation algorithm which is running as the receiver. So the receiver was not assuming ideal channel numbers essentially. So there are some practical aspects that are being modeled, but not all. That is the physical simulation results that we see. And going further, we said from the packet error data, we said we somehow convert it to a MAC layer throughput. So this slide sort of explains what are the things that we do to convert from the packet error data to the MAC layer throughput. So here is the equation which gives the MAC layer throughput. Essentially, this numerator is the number of information bits, denominator is the total time taken. Okay. N is the total number of packets that we simulated. Ri is the number of information bits corresponding to each packet. Si is actually a binary random variable, which is 1 if it's essentially fractals, right? If the packet was dropped, we would make it 0. If the packet was transmitted successfully, we would make it 1. And so this whole information numerator part we get from the simulator, right? We get from the packet error simulation. This is the packet error data essentially. So it is for computing this that we did some form of analysis. Okay. It's pretty straightforward given the MAC layer details of 802.11. How does a typical 802.11 packet cycle look like? Okay. So if the sender wants to transmit a data packet, the sender has to sense the medium. The sender has to initially wait for a period called DIFS value, which is again a fixed value. And after this, it has to do this random backoff. So this time is actually a random amount of time. And after this, at the end of this random time, the sender can transmit the data packet on the air, given that there are no other stations transmitting. Okay. And the time for which the data packet is transmitted obviously depends on the rate at which the packet is transmitted. And once the receiving station receives the packet and decodes it successfully, it would then wait for an amount of time called SIFS, again fixed value, and after which it would send the acknowledgement back. And at the end of the acknowledgement, once the receiver hears the sender hears the acknowledgement, packet cycle is complete. It is ready to transmit the next packet. So this whole process is what we model as TI, combination of DIFS we see. And again, the only random thing here is this random backoff value. So DIFS is fixed. So we take the expected value of the random backoff time. We take the time for which the data is transmitted. We can find it if we know the physical rate from here. And we find SIFS value plus the time for which the ACK transmission goes on. Right? Here we assume that ACK is transmitted at the same rate as the packet is transmitted. And here is how we model the average value of the random backoff. Again, this is fairly straightforward given the details of the MAC layer. Essentially, it uses an exponential backoff algorithm. So meaning each time a packet is failed, it has to retransmit, it has to back off exponentially. That's what it would mean. So this K index here stands for the transmission attempt number. So for the first time, if it's a first time that the packet is being transmitted, this would be 0. It would give a lower value for average value for random backoff. With the first time retransmission, it should be a much higher value. So essentially, yeah.
Just one comment over there. the T-Act, the assumption is the rate is the same as the data, but I think from the standard, it's T-Act goes at, the control thing goes at the lowest level, right? 26 years.
Control
6 and for
that is
6 for 11.8. I think it goes at 6.
actually that is the control part of each packet. There is a control preamble part of each packet. But ACK can go, I think, at any rate actually. But in general, maybe they use a lower rate. That is probably true. But I think I don't think they fix it to 6 megabits per second.
No. I mean, anyway, the preamble says so. It's not.
Right. So, and the thing is,
It can be. So any assumption is okay.
but I think your point is valid that probably just send a lower rate. Just that this is the assumption that we used here. We could have fixed the rate at some lower value.
And then again, you average over K. Is that what you
No, this is actually for fixed value of K. We find expected value of the random backup interval for fixed value of K. We don't average over K.
And what's the fixed value of K?
So that's a good question. So this K value we actually get from the packet simulation data. So how many times did this packet take to finally transmit? At what event was the packet successful? So from that we get a deterministic value of K. So now we say, okay, we get the MAC layer throughput. Now how do we convert it to an application layer throughput? Because finally that's what we are really interested in. We really take the MAC layer throughput, multiply it with the scaling factor. It's very simple, and then get the application layer throughput. This is actually just a constant value, and the way we come up with this constant value is by saying, okay, this is a ratio, and this ratio it's a ratio of the maximum application layer throughput that you can get to the maximum MAC layer throughput that you can get. And this value, the application layer throughput that you can get maximum value, we have the measured results, right? So we get this number as 20 megabit per second. To find the maximum MAC layer throughput that you can get, we use the same analysis that we used before to get this number to be equal to 30 megabit per second. So this ratio is essentially 2 by 3. It could be computed in different ways, but I think this is the approach that we used.
But how do you assume that it's just a scale factor?
Yeah, I think it's a good question. If you have, for example, if you use TCP, it might have retransmissions, and you might have to moderate more closely, right? These are true. We agree. I think we did not actually go into those details. We sort of assume, in general, it would be based on the overhead information, would be a scaling factor. I think without going into much details, I think this is the best thing that we could come up with. Okay. So now, here's again the same block diagram that we saw, but with all the blocks that I've explained, I'll just go through it quickly once more, and we'll see how these different things work. So initially we start with the input, which is the distance value and the environment value. So once we have these values, we apply the standard path loss model. We get an average path loss value. Then we have all this small Rsl measurements, limited Rsl measurements that we make to finally predict the average Rsl value, right? So we get the average Rsl value here, and then we know how to simulate the variations above the average, right? So we get that also. So the idea is that corresponding to any given distance and environment, we sort of generate 1,000 values of this Rsl variation. So this will be the varying Rsl value based on the mean. And then we can similarly, if you use a time window average corresponding to 25 samples, we can similarly get 1,000 values of the Rssi window mean, right? We would need that to do the physical layer mode selection, Based on this and based on the physical layer simulation curves that we saw, that we select a value for each of the physical, so these are the physical arrays that we would select based on this. And here just a minor point, we have used a fading margin on top of the simulation results that we got. We used a fading margin of 8 dB, and this is a very typical design parameter in wireless LAN modems because they are designed to operate in fading environments. So this 8 dB is a very reasonable number that we used. And now we know what is the physical layer rate of each packet, and we know what is the average value of RSI size, right? Based on these two things, from average RSI we can compute average SNO. So based on these two things, we know what is the probability of error for each packet. So this packet error simulator essentially throws a coin and drops packets with that probability number. So these are actually the packet errors. So if the first packet is a failure, this S of 1 would be equal to 0, right? Things like that. Now, one more thing. So to do the packet error simulation, we use 4 dB losses again on top of the simulation curves. This is again to model a lot of imperfections that might be there, channel error modeling, all these different results that we have, and this again fits in nicely with the results. So, and then we saw how do we convert from this packet error data, which is essentially a set of physical error rates and a set of packet errors, to get the MAC layer throughput. That's what the analysis showed us. And finally, we use the scaling factor that we got 2/3 value to convert it to an application layer throughput. So here is our basic throughput prediction methodology. And before I move on, I want to say that if you give a fixed distance value and fixed environment value, the throughput predictor need not give the same throughput application layer throughput every time. Why? There are two random things going on here. The first random thing is actually in this path loss model, there is a shadowing value, right? So shadowing value can be different from run to run, even for the same distance and environment. That is one random thing. The other random thing is actually the way in which this RSI value, this RSI value, instantaneous value varies. That is another random thing. So there are two random things going on. That's why it is always, in this predictor model, it's good to look at not just the throughput number, but to look at throughput statistics, right? Either the mean or CDF and things like that. And that's what we will do in the result section here. So the general approach that we have is that we compare, we want to measure verify the accuracy of the tool that we develop. And to do that, what we do is we compare the statistical characteristics of the predicted throughput with those of the measured values for two different environments, the outdoor line of sight and the indoor non-line of sight. And we show that the values match, and that's how we say it's accurate. There are two approaches that we take to do this. The first one is through throughput CDF. So what we do here is that, so we select a fixed environment. So we say, okay, outdoor line of sight case. We find the predicted throughput value for the same set of distances as we did for the measured values. So it will give you a set of throughput numbers. Now we can find a throughput CDF with this set of throughput numbers, right? We repeat the whole process 10,000 number of times. Why would we get different values each time? As we said, two random things: the shadowing value and the variation. So once we have all this 10,000 CDF values, we can find the 10th to 90th percentile value of the CDF, and we compare with that with the measurements, as we will see next. And the other approach was to use throughput confidence intervals, very similar approach, but here again we find the predicted throughput for the same distance, repeat it 10,000 times. Instead of calculating the CDF, we directly plot 10th to 90th percentile of the throughput numbers that we get, right? And see again if the results are accurate or not. Here are the comparison results for CDF. This is using the CDF analysis. So y-axis is the throughput CDF, x-axis is the throughput numbers from 0 to 20 megabits per second. This is for again for indoor line of sight case. So here this blue curve is actually the throughput prediction results. So this bars corresponding to each curve is actually the 10th to 90th percentile for each throughput value, right? And this star values are actually the measured throughput values. Right? Clear? Yeah.
Could you please elaborate a little on how many parameters you have used to characterize the specific environment?
For a specific environment. So let me just back up a bit and see here. So for a specific environment, I think the most important thing is the path loss model. So it will have a specific value of path loss exponent, like 2 or 3.1 or 1.1.
So exponent is taken from the shadowing?
There is a shadowing value, which is different for different environments. I mean, there is a shadowing parameter there in the path loss model, if you remember. Right.
So the path loss exponent, the shadowing term, and anything else?
Shadowing term and so this could be specific to the environment. So this when we do RSI measurements, we said there is a correction factor that you have to apply. Right. For example, for the indoor environment that we had, correction factor was equal to 4.2, and for the outdoor environment that was equal to 0. So that will depend on environment.
So do you think your model will be insensitive to the Doppler spread?
We have not considered Doppler spread. We have not considered Doppler spread in our model. Yeah. Right. I think that's very true. In the indoor environments that we measured, we think there is no reason for Doppler. We are not moving and environment is not changing, and so we have not considered Doppler.
People can move.
There were no people.
There are no people, so that's
No
the
one's allowed in the
important
building.
He said he measured everything.
Weekends and nights.
Ravi, one question.
Yeah.
You weren't here, so you don't remember.
That 5 simulation blocks, you added 8 dB to take care of the shading.
Right.
That's because instead of you took an AW channel, right?
That is
Why didn't you take a shading channel or LA channel for the simulation?
That's a good question. The thing is, for example, for the outdoor environment, we know it's not a fading channel. We know we have a very clear line of sight path. We know it's not fading.
But for the indoor one, you could have taken.
We could have, but again, what specific fading environment would you take? Would you take a relay environment? If it's a Rssi, what is the K factor? So I mean, it's true. We could have done that. The thing is, we have to do more channel measurements to actually say, okay, here for indoor environment, we can use a Rssi model with k factor equal to 1 or dB. And we didn't do that measurement to come up with that model. So just we said, okay.
Yeah, but when you got that 8 dB margin,
Yeah.
you must have done some measurements too.
Oh,
You shouldn't call it fading. I think.
So this is not based on measurements. This is based on the fact that in typical cards, right, the way they select the rate is so that they don't actually do it for a, they take some AWGN or some curve to actually do, say, okay, for this SNR, I would select this particular rate, right? So they wouldn't do it based on AWGN. They would do it based on fading channel because that is the typical, and they sort of do it for the worst scenario. That it is to consider that we said, okay, it's 8 dB, and 8 is 8. The number 8 is from the fact that it actually corresponds to, I think, 80% service availability for fading for relay fading channel. That's what this number 8 corresponds to. Any more questions? So we'll go back to our the plot that we're looking at. So again, we see that most of the measured values fall within the 10th to 98th percentile of our predicted throughput CDF, which sort of suggests that our method is accurate. The same set of results, CDF comparison for outdoor line of sight case. Again, here are the 10th to 98th percentile values of the predicted, and here are the measured values. Again, we see for most points they fall within the band, within the 10th to 98th percentile values. The next approach, as we said, is using throughput confidence intervals. So here, again to explain, y-axis is the throughput number, x-axis is now the distance points for the various distances that we measure, right? And so similar, the blue curve is actually the predicted throughput. So this bar here is again denotes the 10th percentile of the throughput values measured at this point, 90th percentile of the throughput values measured at this particular, predicted at this particular point, and these are all the measured values. These are all the measurements that we did. So all these red stars indicate the measurements at that particular point. So we see that in general, if you look for 80%, that's why 10th to 90th percentile is sort of 80%, right? For 80% of the measured values sort of fall within this band, 10th to 90th percentile band. That is the thing that we're looking for. That's why we say our method is accurate. Okay. Similar set of results for outdoor line of sight. Again, we see that for most of the points, the throughput, predicted throughput falls within the band. Measured throughput falls within the predicted band. Again, this shows that our method is accurate. Okay. So now, that was for the measured and predicted. Now, using the same methodology that we developed, what we can do is we can say, okay, what is the maximum possible performance that you can ever get if you use a 802.11n modem? What is the maximum possible? So that this is sort of, you can tell the card manufacturer that, okay, you're not doing good, there's a lot of space for improvement, things like that. So this solid multicolored lines that you see here are for the different physical error modes of 802.11a. For example, this blue curve here is actually for the 6 megabit per second mode, and this red curve that you see here is for the 54 megabit per second mode. So we use the same throughput production methodology, except that we fix the rate. There is no rate selection process. We fix the rate, for example, here to get this curve, we fix the rate at 6 megabit per second. If you remember that block diagram, and here we fix the rate at 54 megabit per second for all packets, irrespective of RSS type. Okay. And that's how we get this plot. So if you see the envelope of all these plots would give the ideal throughput performance, meaning. And here is the measured throughput performance, right? There is a huge margin of around 10 to 12 dB between the measured or the predicted and the ideal, what is achievable. And there are various reasons for that. Some of them we think are, one is obviously the rate selection algorithm. This again shows the rate selection algorithm is very critical for throughput prediction or throughput performance, anything. For throughput, anything related to the throughput. So because here we assume that, okay, the card knows what is the best rate now to transmit now. Given this value, what is the best possible rate? That is how we get this cost, right? Whereas the actual thing that we have, actual implementation might not know. And we also took care of this, took into account this fading margin of 8 dB. And this might not be for this outdoor line of sight environment that we measured in. This 8 dB might not have been needed. I mean, we could have done away with 2 dB or 3 dB. Because they don't change those values with environment. The idea is that. And also we account for other losses, which is hard to reduce. But so again, based on this fading margin thing, what we can say is that if we know what environment we are operating in, we could select the fading margin or different parameters and get a better throughput performance. That points to some of the ways in which you can enhance the throughput of 802.11n modems. So I think with that we sort of come to the end, and here are the conclusions, the main contributions that we have made. We think hopefully we are convinced that we have presented a generic throughput predictor for rate adaptive wireless LAN. Okay. So, and this method combines a limited set of Rssi measurements that we have, again a very limited set, and also combines physical or simulation results and macro analysis. We have seen that this method is simple to use. Why? Because it depends only on a limited set of measurements, and this method is shown to be accurate in terms of throughput prediction. And we demonstrated this generic approach using a specific technology for 802.11a modems. And we verified the prediction accuracy by comparing with measurements. We also gained valuable insights into the throughput performance of 802.11a. Right? Second, just want to point out that though most of our work was specific to 802.11a, we want to hopefully it's convincing that this is actually a very generic method. So if you go back to the block diagram that we have, we can just substitute different blocks in the block diagram and work with different rate adaptive wireless LAN standards. For example, if you want 802.11b, the physical layer performance might change, the macro parameters might change, but the methodology remains the same. That is I think, the value of the work that we have done here. So on to some sample applications and future work. Here we have listed some sample applications. Again, this is just representative. This is not a complete list. Most obvious use of a tool like this is in a network planning tool, right? So given a building like WINLAB, given the walls and things like that, we can predict the throughput distribution in each and every place of this building. Right? I think we have seen tools similar to that before. So somebody can actually know where to place the access point, what is the best coverage thing, and all this. We could also use it in building a cross-layer solution when we say, okay, can we select the appropriate video mode for video broadcast or wireless LAN given the link throughput. So this tool will predict the link throughput, and based on that you could select the appropriate video mode. So this is a good cross-layering application for our tool. We could also use this in analyzing new wireless LAN standards. This points to the generic nature of our method of our work, right? It is not specific for 802.11a. If you want to come up with 802.11n, the new standard, we could use the same methodology to predict the performance. Again, we might not have Rssi measurements, but again, those are limited measurements, and if we trade off a bit of accuracy, that's fine. Future work, there are a couple of directions that we have here. There's certainly more. Two of them we have here is in terms of modeling. If you see, what we have done is really to predict the average throughput given a distance and environment. There is another important parameter here, which is actually the second order variation of the throughput. Right? Given that I'm standing here, how does my throughput vary over the next 5 seconds? That is very important, actually. That is a different topic of study. It's very interesting, different topic of study. It should be undertaken, I think. And in terms of enhancement, our research has suggested that if we could do some sort of environment-dependent rate selection, if we know I'm in an outdoor line of sight environment, I could, let's say, get away with the fading margin and transmit at much higher rates and get much higher throughput performance. So I think these are some of the future work directions that we have. And I think with that we come to the end of the presentation. Any questions?